Now that we've kind of got an overview of what redox reactions are, there actually comes a different process, which is how to balance redox equations. I will preface this by saying this looks really complicated at first, and it looks like it's so much involved, but really it's so gratifying because you can actually put a lot of steps together and chain them in a way that it gives you a nice, clean, consistent answer. But first, let's go and talk about how we balance it. In order to balance reactions, we actually use something called the half reaction method. Now, it seems like this is kind of overkill sometimes, but really this is going to be the most consistent way of getting us balanced redox reactions. The half reaction, specifically, is an equation that represents only the reduction or only the oxidation. So, kind of getting some language here, right? Half reaction, well, that's because it's only half of the redox reaction, right? One half is reduction, the other half is oxidation. Combine them to make the whole reaction. For example, looking at this guy right here. So this example here, right, if you see the Ce4 plus with tin, Sn2 plus, and more cerium 3 plus, okay, sure, right? I'm going to balance this. And frankly, right now, it kind of looks okay, doesn't it, right? Because you have one atom of cerium, one atom of Sn, one atom of Ce, one atom. So on both sides, they have the right number of atoms of Ce or Sn. But what's the issue is that if you notice, the number of electrons here are not consistently exchanged. And we have to remember these redox reactions are all about electron transfers, and electrons are still substances. They're still objects that get transferred. They can't appear or disappear, so that you have to keep track of it. So right now, this reaction is actually unbalanced, despite the atoms being okay. Because if you notice, right, Ce is a +4, becomes a +3. Well, again, what happens there is that there's one electron that gets gained or lost here. But then that means on the other side, Sn2 plus, Sn4 plus, there's two electrons that are gained or lost. And right now, it's not consistent, right? We're not showing that the number of electrons gained or lost for either process is really consistent. So we have to do a little bit of work. We're going to use something called this half reaction method. Where first, again, we're at the two half reactions. That's going to take a little bit of practice, but ultimately you find out which substances are undergoing reduction, which substances are involved in the oxidation, and then write each of them out separately. And they're going to balance it out by balancing the major atoms, then we're going to add some O's, or we're going to deal with the O's and the H's, and then deal with the total charge in that order. Now, again, right now, this is not really seemingly going to be making a lot of sense. We're going to see some examples with it in just a minute, but again, just giving you a sense that there is a process to this. It's not just kind of like add stuff, change stuff, do whatever we want. There has to be a very specific pattern. We're going to find the LCM, which stands for least common multiple for the total number of electrons. Combine your half reactions, cancel off repeated species, and then check your work. By the way, the word species, right, and again, most of us see this and we're like, oh, animals, things, plants that are new and unique. Well, that's not exactly what this is referring to. It's just saying which substances are in the reaction equation. All right, so I've recreated these so that you do have this half reaction process that you can always use, so that when we balance these equations, we can have a sense of the process. First of all, the prompt will always be balance the following redox reaction using the half reaction method. All right, so let's figure out what the half reactions are, because that's our first step. Right, the two half reactions. Well, first we got to figure out what's changing. So if you notice, right, cerium, right, this is one substance. So usually, again, we're just going to go ahead and focus on the ones, that are the same atom, right, same element on the left side to see what it does on the right side. So 4 plus here, 3 plus here, and then we have Sn2 plus. I'll do this in another color just for the sake of having that. You can see Sn4 plus. So let's see what process occurred, right? So if our cerium went from +4 to a +3 oxidation, right? So that means it had to have gained a negative electron to go from +4 to +3, right? As a negative electron is gained, that means it is going to be what process? That should be reduction. On the other hand, you have tin, Sn2 plus, Sn4 plus, right? So in this case, we have lost negative electrons, so oxidation is losing, and so that means this is going to be the oxidation process. So right there, I've identified my two half reactions. So let's write them out separately. Let's first do the reduction as Ce4 plus. I'm going to leave off the AQ because that is not as important right now. And then I'm going to do a little bit Ce3 plus. Notice how I've kind of left some space here because there's a chance you have to jot some things in like coefficients and other new substances into the mixture, the reaction. So I'll just do that. And then over here on the right side, I'll do it again with Sn2 plus, right? That's our other half reaction. And then Sn4 plus. Okay, now, normally, again, I would go through and do each half reaction separately. This time I'm writing out the half reactions just to let you know that this is, again, kind of what it's referring to. So there's one half reaction here on the left. There's another half reaction here on the right. Okay, so let's go and go through the process first and complete everything for this one, and then we'll come back and do the tin one. All right, so Ce4+, we're going to balance the major atoms by looking at whatever non-hydrogen, non-oxygen atoms are there, and then put the appropriate number of coefficients. Well, one of each, that part is good. So that half reaction step is taken care of. 2b, add certain number of O's, right? So that the O's are balanced. Well, again, no O's are involved here, so oxygens are already set. Hydrogens here, again, notice that nothing's really involving hydrogens here, so there's no need to worry about that. But finally here, we need to make sure the total charge is going to be sort of balanced by adding the appropriate number of electrons. So in this case, right, the cerium over here is at +4, it becomes a +3 on the right side, so to become +3, we actually add 1 electron to the left side, right? This also is good because, one, it's consistent with the idea that we label this as the reduction process. So this substance over here on the left side has gained an electron. Reduction is gaining an electron. And so cerium +4 plus E- allows us to balance the total charge of this half reaction. All right, so that's the half reaction in the red there for the reduction. Let's do the blue side. So tin over here, all right, let's go through the same process. We're going to balance this half reaction by balancing the major atoms. 1, 1, good there. O's and H's. There's no O's and H's here, so we don't have to worry about it, but we have to worry about the total charge. It is +2 over here. It is +4 over here. So again, how did it become +4 is that we end up kind of losing 2 electrons. So this substance on the left side, right, we lost 2 electrons to become 4+. And we don't represent losing electrons by saying, oh, minus electrons. That's not how equations work, so don't do anything like that. We do it by representing that it goes away. It lost it, so it's another substance over here on the right side because it went away. So the resulting SN4+ is a result of the SN2+ losing these 2 electrons. So this is always written on the right side as losing. Right, so it might be worthwhile just saying losing electrons. Now, right, going through the rest of it, right, we've done the total charge. So now we have 2 balanced half reactions. And then we're going to go ahead and basically combine them. So first of all, though, before you do that, step 3 is find the least common multiple for the number of electrons. Okay, well, we've looked at this one right here. There's 1 electron involved there. This one has 2 electrons involved here. What's the least common multiple between 1 and 2? It's 2. So we need to make sure that the electrons that are gained or lost are the same. And to do so, right, we're going to actually distribute a 2 through this left half reaction. So we're going to do 2 Ce. 2 electrons and 2 Ce3+. We don't do anything over here because it's already 2 electrons there. So again, notice the star of the show at this point is our friend electrons, and now that they're the same number, right, finding the least common multiple there, we are good. So let's finish it off by combining them, right? So we're going to go ahead and take each half reaction to make a whole reaction. So to combine them, you have a couple of ways of doing this, but effectively, you're just going to rewrite it so that all of the reactants are on one side, all of the products are on the other side of a balanced chemical equation. So let's try this out. Let's do this so that I have 2Ce4+ plus 2E-, and then in blue over here, right, because this is a reactant, I'm going to write 2SN2+, right? And then we're going to go ahead and have a reaction arrow for the products. It's going to be 2Ce3+, and the stuff involving tin on the right side, plus 2E-. All right, so again, I'm just copying what's on the left, copying what's from the right on the right, so I have my overall equation. Of course, we're going to have to cancel some repeated species, so a couple of things you'll notice. First of all, this is half the reason why this works, right? 2 electrons on the left, 2 electrons on the right. They're identical on both sides of the equation. They can both be ignored. And then we finally write it out. So whatever's left over, 2Ce4+, right, plus SN2+ yields 2Ce3+ and SN4+. Whew, okay, so that was a lot of steps just to get to this. And ultimately, right, you're like, okay, we just started off with one that, you know, has a bunch of this, and then all you had to do was put 2 in front. Well, again, how did we know to put the 2 in front? We had to know how many electrons were exchanged, and that's where this whole half reaction thing plays in. If we don't know what the half reactions do, right, in terms of number of electrons that are exchanged, we can't accurately balance this whole thing. So we basically kind of do a little thing where we kind of explode the reaction. We split it up. We do a bunch of stuff with each half reaction and then recombine it into one final one that looks nice and clean like that. Now, this again is a process, right, that can apply to more than just this simpler example, right? Notice how we talked about having O's and H's. This one didn't have those, so that made this process a lot faster, but what about one that's a little more involved? All right, so here we go. This is going to be another type of reaction, another subcategory of redox reactions. This time it specifies that we're in an acidic environment. All right, so we'll talk some more about that in just a minute. But many reactions require an acidic or basic environment in order to proceed. And so what happens is that we assume that we kind of balance these out as if they're in an acidic environment. So you'll see that the language will say balance the following equation, right? The reaction equation, balance the following equation when it's in an acidic aqueous environment. All right, so that's getting right there. Already probably throwing some sort of red flags. Oh my gosh, how do we handle that? Well, again, let's kind of see how this process works out. So this would be the prompt that you get. We're going to scooch down here to really see what's up. All right. Now, this is again a straightforward, this is the prompt that you'll have to balance. And then again, like it said in the previous page, it's not recreated here, is that it says to balance it in an acidic environment. We'll see how that plays out. But first, we're still going to follow the same principles as always. Let's find out what's our half reactions, and then we'll go from there. Okay, arbitrarily, I'm going to pick red here. I don't know if it's going to refer to the reduction or oxidation, but I just want to pick stuff up based on that. Now, if you notice, right, what's going on here? All right, I've got MnO4 minus, I've got Mn2 plus. So I know these two are going to be involved in a half reaction somewhere, somehow. I don't exactly know what's going to happen. I just know that these two will be involved because manganese, those are going to be associated in one half reaction. That means iron and iron, right? These two substances here, those are the ones involved in a half reaction. Okay, so let's go and split them up. I don't even care necessarily which one's reduction and oxidation right now. I just know that these two are going to be a part of a half reaction. And then Mn2 plus. Once again, I'm leaving a lot of space here because in case I need to add stuff, take stuff away, change stuff, it can do so. All right, so that's my first half reaction. We'll do the iron one later on. So first, in this half reaction, I'm going to go ahead and balance my major atoms, meaning, right, my non-oxygen. So here's an oxygen there. I don't really care about it. What about manganese? Mn, there's one of each. We're good there. Now, let's balance O's out. We're going to balance the O's out by adding water to the appropriate side. On the left side, I have 4 oxygens. Right? With 4 oxygens on the left, that means I have to, again, kind of balance it with 4 oxygens on the right. But I can't just add O. Instead, notice here it says by adding H2O. So water is a substance here that we can incorporate. We have to add 4 waters, though. Right? I can't just do H2O or just like H2O4. I have to make it so that there's enough waters. So there's 4 H2Os, so there's 4 oxygens now on the left side, 4 oxygens on the right side, so we're set there. 2C. We're now going to balance the hydrogens, right? Before we didn't have any hydrogens, now we do, so we have to incorporate that. But in this case, we're going to do it by adding H plus or OH minus. Let's start off by doing it as H plus. Now with H plus, in this case, right, we have 8 hydrogens on the left side. Right, so just counting out the number of hydrogen atoms, there's 8 here. That means we have to have 8 H's on the left side. But of course, I can't just arbitrarily put H on there. It has to be 8 H plus, right? 8 H plus. And so this, again, is an acidic environment. H plus are associated with that. Done right there. All right, and then finally, 2D was my total charge. Right, for this one, I'm going to add a bunch of electrons to it. The total charge is now, again, going to be counted out by looking at the fact that there is a -1 right here. That's -1. This one has actually a total of +8, right? Because each individual H plus is there, but there's 8 of them, so it's +8. That means in total there's +7, right? So that's +7 here on the left side. What about Mn2 plus? Well, Mn2 plus, that's a +2, right? H2O, that's 0. So that means over here on the left side, it is +2. So we went from +7 to +2. +7 to +2. What had to have happened is that the electrons are gained by the left side, right? So that means we had to have we had to have a gain of 5 electrons go from +7 to +2. So those 5 electrons get added right in there. Okay, so again, looking at this one right here is kind of its own separate balancing, going from +7 to +2. All right, so that half reaction now is done for our friend manganese. Now for the other one, I'm going to do it underneath it just because it's here. Let's go ahead and do this with our Fe2 plus. We're going to make Fe3 plus. All right, let's go through the process. Balancing major atoms. Well, Fe, there's one of each. We're good. There's no O's to balance. There's no H's to balance. So finally, total charge. All right, so we're going from a +2 to a +3. How'd that happen? Well, again, in order to make the charges work out, you have to add a certain number of electrons. I can just add 1 electron here on the right side so that +3 plus a -1 gives me +2. All right, so now my charges are balanced on both sides, and so here I have a good old balanced half reaction. Step 3, find the least common multiple for the number of electrons. So the least common multiple, right? So I'm comparing this guy to this guy. So 5 versus 1. What's your least common multiple? It's 5. So I'm going to distribute a 5 through all of this. So that means the result will be 5 irons and 5 irons and, let's try this out again, 5 electrons. So now that that's set, that's step 3. Step 4, combine your half reactions and cancel your repeated species. So let's put them all together. All right, so one more time. And we know that substances that appear identical on both sides, we can effectively cancel off. So I can already see that the 5 electrons here and the 5 electrons here are going to go. So those can go. All right, but let's go and jot in whatever's left and see if there's any need to cancel. So MnO4 minus plus 8H plus, and then for the iron side, Fe2 plus, and that's going to yield whatever's in red, Mn2 plus 4H2O plus 5. Let me do some blue again. Excuse me. Plus 5 Fe3 plus. Okay, and that's effectively it, right? So there's nothing else here that needs to be canceled off. We have the right numbers of each atom, everything seems set, and all the charges are balanced. The very last thing about this is that you'll find that our friend here is balanced in an acidic environment. So you remember the prompt, right? We can do all this, that's great, but what exactly does it mean by being in an acidic environment is that you do have some H pluses around. Remember that H pluses are affiliated with acids, and so this is an environment where there's a bunch of H pluses that are involved. How it actually plays into it and how exactly the exchange happens, we're not really too worried about. Just know that at this point, this is how you would balance it. All right. You see here you have a couple more examples. This one involves chlorine and chromium, so take your time through that one. And then finally you have this one right here, which has what looks like a lot more stuff. But again, once you follow the principles that you're used to, you'll find that it actually follows everything that you need to be able to do. All right, finally, I'm going to scooch here to where you have this idea of balancing redox in a basic environment. So in this case, right, we have what we've done so far is everything in an acidic environment. So we're saying here, if a redox occurs in a basic environment, first, you want to balance it as if you're in an acidic environment, like we've been doing over and over again, or like that's what we've learned so far. And so to turn it basic, you're just going to add enough hydroxide ions to neutralize whatever H plus ions are present. Okay, so this is again going to be a little bit tricky, but one of the great things about this is that we can go ahead and take something we've already done. So this one, Cr2O72 minus plus CO minus chromium. This one's already been balanced for in a previous example, and this is what the answer is going to be. So this again is being balanced as if it's in an acidic environment already. We've done this already, or at least we assume we can do this already, and so this is a balanced redox reaction in an acidic environment. So now what we're going to do is that we're going to, again, to make it basic, add enough hydroxides so that we can neutralize the H's. Now, how many hydroxides will you need to add? Well, on the left side, if you look over here, my acid substance has the H+, I have 14 of them. So I'm going to add 14 OHs, right, or 14 hydroxides, okay? Well, again, because anything I do on one side, just like any other math equation, I have to do the same thing on the other side. So I'm going to add 14 OH minuses over here as well. All right, so what happens when you combine 14 OH minus 14 H pluses together is that you end up making 14 waters, right? So again, this combination of these two is going to result in 14 H2O. Now, again, that's kind of not really a problem per se, but if you notice, right, you have 14 waters that you make from those two. You had 7 H2Os that are already there as part of the balanced equation. So again, like I said, we cancel off species that appear on both sides. Since there's 7 here, there's 14 here, we can actually get rid of these 7, and then this actually then just becomes 7 H2O. All right, so then the resulting substance, or the final equation anyway, becomes Cr2O7, 2 minus, plus 6Cl minus, plus the 7 waters that were created. And that's going to produce 2 Cr3 plus and 3 Cl2 and 14 OH minus. And there we go. So now we've balanced it so that it's in a basic environment because it does have hydroxide ions now, which is characteristic of basic situations. Okay, that'll do it.